All right, so what we're going to be doing today is more of 3.7, which is building strong roots. And we're going to be starting with the quadratic, and then we're going to move to cubics. Okay, so the directions for, sorry, I keep scrolling up and down, but it says find the roots of each and identify whether the roots are real or complex or imaginary. And we talked about complex and imaginary are these numbers that look like this. They have i's in them, or they have square roots of negative numbers in them. So I really wanted to talk about this one because this is our first case that we've done together. You've done this before back in integrated 2, maybe. But either way, I want to make sure that we all get this. Okay. So the very first thing that whenever they're asking you to find the roots, they're really asking you to find where the x-intercepts are. And you're like, Ms. Johnson, this doesn't have any x-intercepts. You're right. So because this doesn't have any x-intercepts, we can now say that the roots are imaginary. Okay, our roots are imaginary. What does that mean, Ms. Johnson? It means that this parabola does not intersect the x-axis in the real plane. Okay, on the real plane. What do you mean by the real plane, Ms. Johnson? Well, if you remember from last year, maybe, that you learned about there's something called the complex plane. The complex plane is where we can graph and look at imaginary numbers. So it looks exactly like the real plane, except for this axis is called the real axis, and this axis is called your imaginary axis. So it works and functions exactly how you already understand it. We relabel these because now we're dealing with imaginary numbers. So someone asked in the chat, so when a problem doesn't have x-intercepts, I'll change that to when a parabola doesn't have x-intercepts, meaning it doesn't touch the x-axis, the roots are automatically imaginary. And the answer is yes. Okay. And so here's how you find them. Okay. So you can find them in many, many different ways. Because I already know that this is imaginary, I'm not going to go at it factoring, because factoring, like if you're not used to factoring using imaginary numbers, then factoring becomes more of a task than it is understandable. You can use completing the square, or you can use the quadratic formula. Okay. Quadratic formula is what we did up here, right? The quadratic formula is this is when I sang to you guys, remember, x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And then you just plug in your numbers. Okay. So this is one way to do it. Because I've already shown you how to do this way, I think I'm more prone to using completing the square for this one, just so you have options and you could see which one you like better. Things you should know about completing the square and quadratic formula, they work. You can use them on any quadratic that you want. You can use them on any quadratic you want. The thing about factoring, like this one, I think we factored, right? Yeah, x squared minus 4x plus 4, we factored it to get x minus 2. You can only factor things that are factorable. And I know that sounds silly, but if you haven't factored using imaginary numbers using this one, again, it becomes more of a task. So I am going to complete the square. So I have a couple of videos about completing the square that you guys can watch, but I'm just going to give you the behind the scenes kind of thing. So the very first thing I do is I draw x squared. X squared is literally a square. Okay, so I draw a square. These negative 4x's look like little rectangles like this. Oops, that's not a rectangle, guys. There, they look kind of like let's leave it like that. Okay, so it's supposed to be that it's the same height, right? And I have 4 of them. So again, when I say complete the square, I'm literally trying to make a square. I'm literally trying to make a square. So I'm going to put 2 this way. Oops, I'm going to put 2 this way. And because I'm trying to make a square, then I'm going to put 2 this way. Do you see how I'm building my square here? This is the concept behind it. And I am going to take the time to do this because a lot of people, they know how to complete the square, but they don't actually know what they're doing. So it's kind of like lost on them. So does everybody kind of see how my square is being built? Does everybody see this? And if you were in my class and we were using actual tiles, I tell you to push these tiles together, but I'm trying to show you that they're like a little bit separated so you see that. Now, does everybody see how this is almost a square? Does everybody see how this is almost a square? Good. So you see how this is almost a square, but what? I'm missing these little pieces here. How many little pieces go here? How many little pieces go here? Again, it has to be a square, and the little pieces look like little tiny squares. They look like this, maybe. I don't know. Maybe that's too small. Let's see. Yeah, that's too small. Let's make them bigger. Stop it. I want to grab the corner. All right, you don't get to stay. I need a square that's like that wide and that tall. Does that make sense? Yeah, that's what I want. So I need, how many of these squares would I need? Yeah, not 5. So some of you said 5. So I'm going to arrange my 4 squares just so you see where they go. Do you see how they line up right here? They go 2 by 2. You guys all see this? Don't do it. Sorry, this I usually don't draw all of these squares, but for the first time, because you guys haven't seen this in a while, I'm going to do this just because this needs to be a picture in your brain. Do you guys all see how that's a square? Can you imagine me pushing these all together and it forms a complete square? Yeah, very good. All right. So yes, it is. There are 4 little guys right there. Does everybody see that? Then I'd ask you, okay, well, how long is this side? And you'd be like, oh, that's X and 2. And because this is minus 4X, then I'm going to make this X minus 2. Does everybody see X minus 2? The length of this is X because this is X long. And then these are 2, 1, 2. Does everybody see that? Good. How long is this side? How long is this side? Yeah, it's X minus 2 again. Very good. Okay. So then I put X minus 2. Notice I put the minus right next to the 2 because I need to not lose that guy. I don't want to lose that negative at all. Very good. All right. Very, very good. I'm just grabbing some stuff here. Okay. Okay. So then the next thing that I do is I write this out both as a product and as a sum. What? So I write it out as a product, meaning X minus 2 quantity squared, right? Because it's X minus 2 times X minus 2. Again, hence we're doing complete the square, and it's a square. Do you guys all see that? So it's literally a square, and this is a squared. Okay, so that's why it's called complete the square. And then I write it as a sum. What does that mean, Ms. Johnson? This is X squared, so I write X squared. I have 1, 2, 3, 4, right? I have 1, 2, 3, 4 X's, so minus 4X. And then I have 4 little guys, plus 4. Okay, so I wrote it as a I wrote it as a product and I wrote it as a sum. Come on, little guy, catch up to me. There it goes. Okay. So the next thing I'm going to do is, you can notice, you're like, but Miss Johnson, this doesn't match this. And I'm like, you're right. So I'm going to write that right beneath it. And I write X squared minus 4X plus 5. Now here, if you notice, I'm like, X squared matches X squared. Check. Negative 4X matches negative 4X. Check. Yay. Oh man, but 4 doesn't match 5. So your brain should be saying, how do I get from 4 to 5? What do I need to do to get from 4 to 5? Anybody? How do I get from 4 to 5? Yeah, just add 1. Someone said, how would you know how to make this square for different problems? So Honestly, I am showing you different ways to do the same thing, right? So, you know, like I'm still doing the same thing. If I would have done this using the quadratic formula like this up here, I would get the same exact answer. I'm showing you a different way because some of you are like, ugh, that quadratic formula. I need you to have alternative ways to do the same thing, right? So if you think about anything, the more ways you understand the more ways you know how to do one thing, the more you understand that thing. Does that make sense? So very good. You would just add one. Good. So I'm going to add one, right? Add one and I get 5. But I can't just add one to one side. I'd have to add one to the other side. So be careful. We're adding one to the whole thing. We're not just adding one to the -2 because that'll mess it completely up. And so I'm saying that this is x minus 2 quantity squared plus 1. So if I factored this, I would get x minus 2 squared plus 1. And you can kind of see this now, like can you think about division? Because we've done division, right? Do you see this as a division problem that we divided x minus 2 by this, and we got our answer as x minus 2, and then we had a remainder of 1. Do you guys all see that? Do you see how this is all connecting? You should also recognize this. Does anybody recognize this? Does anybody recognize this? If I told you to graph this, would that be easy or difficult? I don't like the word easy, but you know what I'm saying. Good. If I told you to graph this one, a little bit more difficult, yes? So the reason why we like graphing this one is because the shifts are very obvious, right? This is actually called a vertex form. And you guys all like graphing from vertex form because you're like, oh, Ms. Johnson, I remember how to do this. Right 2 because it's in backward line up 1. Perfect. So there's a lot of useful things that are showing up when I know how to do completing a square. Okay, so that being said, now I've rewritten this thing to be equal to this. Now I can solve this thing. So solve it for what, Ms. Johnson? Well, solve it for y equals to 0. Solve it for y equals to 0. Okay, so okay, so now that I'm solving this for y equals to 0, why are you doing it for y equals 0? Because it asked me to find the roots, right? And so roots are x-intercepts, right? And what's an x-intercept? It's when y equals 0. So I'm trying to find the roots, meaning set this guy equal to 0, Ms. Johnson? Yes. Does everybody know why I'm about to set it equal to 0? Because nowhere does it say, Ms. Johnson, set it equal to 0. Does everybody see where I'm getting equals to 0? Yeah, good. So if the reason why, again, is because you guys all said, hey, Ms. Johnson, to find the roots, you need the x-intercepts. I'm like, but it doesn't have x-intercepts. And then you guys said, oh, then that must mean they have imaginary roots. Very good. So when we're trying to find the roots, we will always set it equal to 0. Equal to 0. Where is it? Where's my, oh, I didn't even write it, but it's equal to 0 because look, this is the line, y equals to 0. And over here, oh, we just wrote them because we stole them, right? So again, equals to 0. So whenever they ask you for the roots, your brain should say, oh, that's a synonym for solving it for equal to 0. Okay. So right here, I'd rather solve this equation than this equation. Right here, I'd rather solve this equation than this equation because I could just use SADMAP. You guys all got that? So Ms. Johnson, does everybody remember what I mean by SADMAP? SADMAP, does everybody remember SADMAP? So SADMAP says, hey, is there any subtraction or addition on the X side? Right? And you're like, yeah, Ms. Johnson, -2 and +1. Well, technically that -2, he's all the way stuck in that parentheses and I can't skip a step, right? So I got to go with this guy right here, this add 1. How do you undo adding 1? How do you undo adding 1? Very good. We just subtract 1. Very good. Very, very good. So then we still have this x minus 2 quantity squared equals to -1. Everybody okay with this? All right, so now what would we do? Anybody know what we do right here? So no, we don't have any division or multiplication, Miss Johnson. There's none of that. There is an exponent. How do I undo that exponent? Very good. Yeah, exponents for sure. Good job. How do we undo that exponent? Very good. Yes, we square root. Okay, go ahead and square root it. I'm going to give you a couple seconds to do it on your own because I want you, there's something that you have to remember. There's something that you have to remember. And if you don't remember it, literally your answer is not right. So you have to remember something because even on your calculator, it won't show you. Okay. Did you do it? Yes. Someone says, hey, Miss Johnson, isn't the square root of -1 imaginary? Very good. Very good. So you should have 2 answers. See this 2 right here, the squared? See this squared right here? He's reminding you, hey, you should have 2 answers. Do you have 2 answers right now? If you don't have 2 answers, you just did it wrong. And I got you. Not just kidding. So whenever you take the square root, you also have to, yes, someone said it in the chat. Very good. You have to include plus or minus. So if you did not include plus or minus, put a big old plus or minus here to let yourself know that. Ms. Johnson, where does the plus or minus come from? Okay, so the plus or minus comes from here. So if I said, hey, I have a number, and when I square it, it's 9. So I have a number, and when I square it, it equals to 9. I say, what's the number? What number could go in there? Yeah. So if you didn't say -3 or 3, then you're wrong. Hey, Miss Johnson, if I forget, will I be marked off? Yes. Right? Because I'm looking for 2 answers. You give me 1 answer. How can I give you complete credit for that? Right? Here's the problem though. If I take this, right? If I take this to Desmos, my best friend, right? Desmos is limited. Calculators are limited because they're function based. So if I go square root of 9, why does it only give me 3 as the answer? Why doesn't it give me 3 or -3? Well, number one, because calculators are functions, meaning you ask it for something, it can only give you one thing, even if there's multiple answers for that thing. Second reason is because see how I didn't take the square root of 9, that was the problem. The problem was the square root of 9. We call that the principal root. The principal root will always be positive. Now, if I say, okay, Ms. Johnson, so I want you to solve x squared equals to 9. So there's x squared. And then I look for 9, which is right here, right? This guy right here, I'll write a line, y equals to 9. Why do I have 2 answers here, but I don't have 2 answers here? Well, that's because, again, your calculator is a function. It's functions, meaning it can only give you 1 answer at a time. Your job as the really, kind of wise human being, because you can think, your job is to remember whenever you take the square root, you have to include plus or minus. I'm going to say that again so it's obvious on which part is it. So, Ms. Johnson, how come we didn't have to do that for like remember when we were simplifying like just the square root of a number, like the square root of 20? How come we didn't have to put plus or minus? Because you didn't take the square root. The square root was given to you already, embedded in the problem, right? Here, does anybody see any square roots here? No. Whose great idea was to pull in the square root? That was yours, right? If you scroll up to the chat, I said, okay, well, how do I get rid of the squared? Who said to get rid of it using the square root? You did. So if you bring in square root, you have to remember plus or minus. So if you are likely to forget this, then you need to use the quadratic formula, because you won't need to remember it because it's embedded into our formula. Do you see that? But I'm just going to tell you, I like this better because it's a lot quicker. Like, look at my work. It's this, and it doesn't look like a mess like this. And if you mess up once, okay. So I'm going to continue. So I have x minus 2, because these two undid themselves, right? X minus 2 equals 2 plus or minus the square root of -1. Now over here, I'm thinking about like, oh, Miss Johnson, I remember you telling us this, that the square root of -1 equals to I. The square root of -1 equals to I. So in a second, I'm going to replace that with I. Okay. So last but not least, I will be adding 2 to both sides. Add 2, add 2. Do not fall into this trick. X is equal to, can I add 2 and this square root of -1? Can I add these two together? Everyone say yes or no. Be wrong. Who cares? It's okay to be wrong. Yeah, you can't. Anybody know why you can't? Why can't you? Why can't you? Okay, so I'm going to just say, when you guys are making your flip grids, when you move to this is what you do, this is why you do it, that's when your videos become that much better. Okay, and as a human who needs to communicate, soon to be adults, right? The biggest thing that you want to hear is why. So when you watch social media, when you watch commercials, when you watch anything, any really good video is going to tell you not only what to do, but why you should do it. Does that make sense? Yeah, in this, essentially, these two are not like terms. That's the easiest way for me to put it. Ms. Johnson, they're not like terms. Yeah, like terms mean same variable, same exponent, or same base, same exponent. This has a base of 2. This has a base of square root of -1, right? Or -1, right? So then you're saying, oh, but Ms. Johnson, how come you can add 3 plus 4? They don't have the same base they don't have the same base. Yeah, but they do have the same exponent, or you can think about them having x to the 0. And it's a constant, so you can think about them being the same. So because these aren't the same, I cannot add them together. So then I write 2 plus or minus I. Please don't think this is some like hybrid number. This is like some mutant X-Men number. It's not. It is just 2 plus I and 2 minus I. 2 plus I, 2 minus I. Those are your two numbers. So there's my roots. 2 plus I, 2 minus I. Okay. And these are called complex. Complex means it has a real part and it has an imaginary part, making them a complex. So you can call this imaginary, you can call this complex. So is everybody okay with this idea? You can use completing the square, or if you would have done this using the quadratic formula, somewhere in here, you would have gotten the square root of -1. Somewhere in here, you would have gotten square root of -1. And that is why it doesn't matter which way you use. So some of you are like, man, I like completing the square so much better. Good, use it. Some of you are like, no, I hate complete the square. Please give me quadratic formula every day of the week. Great, use that way. Notice here, they're the same thing. Okay, they're the same thing. It's just different ways to do the same thing. Okay. All right, with that being said, we already answered this one. So what strategies did you use to find the roots of quadratic equations? Can you guys name some of the strategies that we used? Can you guys name? Yeah, I will tell you right now, for those of you who make small mistakes like I do, this to me is a lot more accessible, because there's less places for me to make small little errors. Do you see how many like little errors Miss Johnson, like, you know, Miss Johnson, she makes errors. So do you see how many little places Miss Johnson can make an error, right? And especially for those who struggle with substitution and you're not sure if that negative is that negative, you should consider using completing the square. And it's just a matter of you practicing over and over again. Very good. Okay, so how did we solve it? Someone says quadratic formula. Someone said completing the square. There's one more way that actually there's two more ways that we came up with. There's two more ways that we came up with. Yes, and factoring. Very good. There's one more. Yes, thanks. Yeah, you guys came up with all of them. And I'll type them here so that you guys all have access to them. And then there's benefits for each one. You have to figure out which one you like the best. I tend to use factoring first. If that doesn't work, complete the square. Actually, sorry. Before I do factoring, I'll use the graph. Factoring, and then I'll complete the square. And then I will use the quadratic formula. So each of them have their advantages. The graph and factoring are your most quickest ways to do things, right? But the problem with them is they don't work on every single one. The best parts about completing the square and quadratic formulas is that they work on every single one. But the problem is sometimes it could be a little bit lengthy, right? My suggestion, I put it in the wrong place. My suggestion is that you familiarize yourself with that. If you are using one of these apps that just show you the answer, that's great and everything. But it's not helping you become a stronger learner, right? Why is it imaginary or complex? Very good. So this one's complex because the parabola actually never touched your x-axis. So these roots, if I graphed them, they would be in the complex plane, but they would not be in the real plane. This is why they're not touching. Okay, very good. All right. So then it says using work from problem 1, write each of the quadratic equations in factored form. And when you finish, check your answers by graphing when possible and make any corrections if necessary. So we've already done this one. I think we did the first two already in factored form. No, we didn't. Okay. So looking at this picture, can you write your function in factored form? Here's the function right here. You can kind of see it. Let me go down. Oh, you can't see it. Let me get one thing smaller. So can you all take a second to write this in factored form? It should take you literally 3 seconds. 3 seconds it should take you. I'm going to pause really quick in there. Okay, here we go. So to write this in factored form, either number 1, you're factoring this, but I don't have to because they gave me the graph of it. And so to write it in factored form, I'm literally taking my x-intercepts, which in this case are, it says 2 and -3, and I'm writing it in factored form, making it look like this: x minus 2, x plus 3. Okay, that's my factored form. Now, if you're wondering, Ms. Johnson, why is it opposite? Well, because if I set this equal to 0, right, and then I use my 0 product property, I would get my roots as 2 and -3. So that means that the factored form is going to be x minus 2 and x plus 3. Okay. So I'm going to copy this so I can put it in my answers down there, where we're actually trying to work. Really? I guess I shouldn't have copied it. Come on, friend, come with me. All right, so here, this is this, right? And then to factor B, let's look at B here, this guy right here. Oh, Miss Johnson, how do I write the factor? Like, it looks so crazy. So you're going to take the same idea here and put it here. So the very first thing I'm going to do is I'm going to separate out these roots, right? I'm going to write 1 plus 2 root 2. I'm going to write 1 minus 2 root 2. Now this is a practice, right? I want you to be wrong. Okay. So I'm going to scooch this over this way. And I want you to attempt at writing the factored form using these 2 roots here. Okay. I want you to try. If you don't get it right, shoot, I'm glad you got it wrong. You're like, Ms. Johnson, you're glad that I got it wrong. Yeah. Heck yeah. Because if you get it wrong here and you reflect on why you got it wrong, then that'll be your strength during your final. But if you leave it as a weakness, I mean, that's why that might be another question that you got wrong. Okay, so I'm going to give you like a minute to figure this out, just to figure this out. And then check your answer like how I showed you here. So solve x minus 2 for 0 to make sure that you get back to your roots and make sure they're correct. This is something I really need you to put pencil and paper to, because again, if you understand this one connection, when I move over to cubics, which that's what we're going to do down here, then it'll make complete sense. But if you don't get it with quadratics, then we're going to be in trouble. All right. So I will stop talking. You're going to start writing. Go. And don't put your answer in the chat yet. Just wait. All right. So pencil to paper. If you tried this one was tricky. This one was like straightforward. Oh, x minus 2, x minus 3. So I'm almost going to go backwards just so that you guys see how I think about this. So I think about this as x is equal to 1 plus 2 root 2. And x is equal to 1 minus 2 root 2. Okay. The next step above this, right? Above this one, because this one over here, this step right here says x minus 2 equals to 0, x plus 3 equals to 0. And then I solve, right? And I get x is equal to 2, and I get x is equal to negative 3, right? So I'm going to go to this step above where 0 is on one side and x and the numbers are on the left side, okay? So here I am right here, x is equal to 1 plus 2 root 2. The line above this, I want it to say equals to 0. I want it to say equals to 0. So it's almost like I'm moving up, right? So how would I move this stuff over? How would I move 1 over and how would I move 2 root 2 over? What would I do? Yeah, I'd subtract off the 1. Very good. Yeah, and I'd subtract off the 2 root 2. I'm almost thinking about these two as separate because that's the way my brain works. Now, if you think about this as one big gigantic thing, just remember that individually they have to look like this. X minus 1 minus 2 root 2. X minus 1 minus 2 root 2. Does everybody see that? Good. Your turn. I know I just gave you some time, but I want you to try. If you didn't get this part, try to get this one. Again, I just want it to say equals to 0, and I want this to be moved over here. Your turn. Attempt this. Like really do. The more you put pencil to paper, the more you're going to understand this. Okay, so you guys attempted to do this. Very good. So we're going to go with, I'm going to subtract 1, Miss Johnson, and I'm going to add 2 root 2. Very good. So this would say x minus 1 plus 2 root 2. Okay. And if you remember these two numbers, just for argument's sake and definition's sake, please remember that these are called conjugates. These are called conjugates, right? Conjugate means, so if you think about when you conjugate a verb, like I'm taking you back to like Spanish class or whatever language that you learned. Like if we conjugate the word comer, right? It's como, comes, come, comemos, comen, right? So the COM stays the same, and then we change the ending to kind of tell us who is eating, right? So here, if you notice, the 1 is the same. The 2 root 2 is the same. Then we change, instead of the ending, we're going to change the operation, right? From plus to minus. Okay, they're not opposites, because if they were true opposites, this one would be negative. One of these ones would be negative, right? But they're not. They're called conjugates. So conjugate means we keep the terms the same, 1, 1, 2 root 2, 2 root 2, and we change the operation. How does that help us? Because we know that something special happens with conjugates. Something special happens with conjugates. Okay, so Ms. Johnson, we're still not at factored form. Okay, but we're right here. We're almost done. We're at this point right here. So then I'm going to stick these two in parentheses and set it, well, I don't have to set it equal to 0, but I'm going to stick these two in parentheses. So you want me to stick this whole thing in parentheses? Yes. Yes, absolutely. So here goes my first one, my second one, x minus 1 plus 2 root 2. And then my first one was x minus 1 minus 2 root 2. Okay, so this is factored form. So run it through me, run through this with me one more time. So how did I get this? First, I looked at my roots, right? And then I wrote it as x equals to the first root and x equals to the second root. How did I get from here to here? Now notice we went backwards. How did I get from here to here? What did I do? What did I do? Yeah, I basically solved for 0, and that sounds really weird, right? I basically solved for 0, or I took everybody and put it on the x side, right? It's kind of weird because you never solve for 0, but that's exactly what algebra is. Algebra is like you taking something and manipulating an equation so it looks the way you want it to look. So I wanted it to look like this, equals to 0, equals to 0, right? So then, so that makes more sense. Okay, how did I go from this step to the previous step? Our answer. How did I go from that step to the previous step? What was my last little step there? Yeah, I just stuck them in parentheses. That's it. I just stuck them in parentheses. So is that true for every single one? Uh-huh. So guess what you're gonna, oh, we already did this. This is in factored form. Oh, I didn't copy it. Hold on a second. Let me copy this. Let me see if I can copy this better. If I copy here and I paste here, does that work? Look at me. I learned something new. Okay, same thing goes with this one. This is in factored form. That's not what I wanted, but thank you. I want just this. Why are you doing that? Oh, I know why. Because I keep telling it that's what I want. Okay, so I want this. This is in factored form. Right. And this last one is the one that I want you to try. Can you try writing these? Now go through the same steps that we just went through. I'll start you off. I want you to try writing those. And then you'll see a pattern and then you'll be like, oh, I understand why she has us doing it like this. So x equals 2 plus I and x equals 2 minus I. So I want factored form for both of those. So go ahead and try that. Okay, so again, all I'm going to do is I'm going to solve for 0. Again, that sounds really weird. So I'm going to subtract 2 and subtract I. If you can get to the place where you do some of this work in your head, and I know that sounds weird because most of your math teachers in the past have always been like, show your work, but some of this work you do not need to show me. I know you know how to subtract, right? I'm guaranteeing you know how to subtract. So some of this work should be happening in your head so that it'll free you up to do this. So I subtracted 2, boom, I added I, boom, I subtracted 2, boom, I subtracted I, boom. And then I just take those two things and I put them in parentheses, x minus 2 minus I, which is what a bunch of you already told me. Thank you so much. And then I'm going to copy and paste this as soon as it shows up. Come on, buddy, you can do this. Okay. Huh. Huh. Why are you not grabbing everything here? Let's try again. Rawr. Yay. All right, so there's all of them. We wrote them all in factored form. Based on your work in problem 1, it says, based on your work in problem number 1, would you say the roots are the same as the x-intercepts? And that's what we talked about. So the answer is yes. And it says, based on your work in problem 4, what's the relationship between roots and factors? So I need a sentence from you. I need a sentence from you that tells me that you understand this. What's the relationship between the roots and the factors? So let's scroll. Let's take a little, gander. What's the relationship between the roots and the factors? What's the relationship between the roots and the factors. What's the relationship between your roots and your factors? And then what's your relationship between the roots and your factors? So I need a good sentence. This is like the key part of our lesson here. If you understand this, then cubics will be exactly the same, just with another level. So give yourself probably like 35 seconds to write yourself a strong sentence that tells me how the roots and the factors are related. So we have some really good sentences. Some people say we use the roots to find the factor, so we solve for 0. Very good. So this person says, hey, Ms. Johnson, I'm just going to describe to you what we did. We used the roots to find the factors. Exactly. Someone else said, both the factors and the roots solve each other. So here's the roots and here's the factors, and we use them to get to each other. Very good. So over here, if you notice, or am I here? We use the factors to, we use the roots to get the factors. Okay. For all of these, we use the roots to get the factors. Sometimes we'll use the factors to get the roots. So very good. I'm just going to collect some participation points. Very good. So if you don't have that relationship down in your head between how do I get from here to here, or how do I get from here to here, that's huge. Okay. So I want to like make it concrete for you. So let's say I drop you off at Target. Are you able to get back to school? Okay. And then if you're at school, are you able to get to Target? Right. So that's what I'm asking. If I put you here, are you able to get here? And you're like, yeah, that makes sense. Because look, all I have to do is set each place equal to 0 and then just solve. Very good. So if I start you at school, are you able to get back to Target? And you're like, yeah, I kind of just have to do the inverse in reverse operations. Exactly. Right. Okay. Very good. Sorry, I'm trying to hustle. Okay. So now what we're going to do, we are moving to cubics. Yay. Everyone say yay. Yay. Okay. So how does all of what we talked about apply to cubics? It's the same thing. The same. What does that mean, Ms. Johnson? Oh, let me show you. Okay. So now let's take a closer look at cubic functions. We've worked with the transformations of x cubed, but what we've seen so far is just the tip of the iceberg. For example, consider this: x cubed minus 3x squared minus 10x. Now, imagine I didn't give you this graph and I said, hey, find me my roots. And you're like, what? So then we would go back up here and you guys would say, okay, Ms. Johnson, I know how to do this. You told us that we can use graphing, we can use factoring. Now, Ms. Johnson, can I use completing the square and quadratic formula? Kind of, but not right off, because the quadratic formula, guess what, only works on quadratics. Someone said quadratics. I heard you, even though I didn't hear you. Yeah, that is correct, Mr. Russell. You're correct. I didn't realize that until right now. Okay, so the very next thing that happens is that, okay, so if I gave you this picture, which method would you use? Would you use graphing? Would you use factoring? Because Ms. Johnson, you told me that I can't technically use the complete the square or the quadratic formula right now. You're right. So which one would you use? Right? Yeah, I'd use a graph. Okay, good. So find me my roots. Everybody go look. So you're like, Ms. Johnson, it's right there, and right there. Good. So some of it looks like if I zoom in and put my eyeballs next to my screen. Thank you. I appreciate it. Yeah. If I zoom in, I can see that this is probably -2. This is probably 0. And this is probably 5. Okay. So use the graph to find the roots of the cubic. Use the equation to verify that you are correct. Okay. So first, let's write down our roots. You guys all said, what did you guys say? 5, 0, and -2 are my roots. And then it said to use the equation to verify. Now, what does that mean? If I plug in a 5, when I plug in a 5, what should I get out? When I plug in a 5, what should I get out? Yeah. If I don't get a 0, I did it wrong, or it's not a root, right? So let me bring my handy dandy best friend. Where's my best friend? My best friend was one of these. Oh no, I lost my best friend. There it is. I found it. Sorry. Here's my best friend. I'm going to X all these out. I'm going to I'm not going to plug in x cubed minus 3x squared minus 10. I'm going to like actually plug in my 5. So 5 to the third minus 3 times 5 squared. Oops, I wanted the parentheses here, 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 there. 3, 5 squared minus 10x, minus 10 times 5. Okay. Oh my gosh, you guys, look, I got a 0. Everyone say yay. Yay. Okay, why are we saying yay, Ms. Johnson? Because the graph and what you observed on the graph is correct. When I plug in 0, I'm not even going to plug it in, right? Because 0 minus 0 minus 0 is 0. I don't need that, right? Let me try -2. Let me try -2. So I'm going to plug in -2. I'm going to plug in -2. See why Desmos is my best friend? Desmos is my best friend because look, oh, it gave me 0. And then I don't even have to worry about Ms. Johnson calculating incorrectly because guess what? It just worked out correctly. So is everybody good on number 1, finding my roots for a cubic on a graph? And number 2, verifying that it's correct using my equation. Is everybody okay with that? Because this is like extra points on your next test. Now, don't think extra credit. I mean, like you did something wrong, you checked it, and you're like, shoot, I would have got that wrong if I didn't check my answer. Right? Again, I'm trying to convince you to check every single answer. Okay, moving right along. Write g of x in factored form. Wait, you want me to write g of x in factored form? Wait, Ms. Johnson, you just showed us how to do this, right? I just showed you how to do this. Okay, so wait, let me remind myself. Oh, yeah. You guys told me that if I wanted to find their roots, I can find my factors. Oh, yes. Okay, so pause really quick. And now give me my factors based on these roots. I'm going to pause you really quick and do it. This is pencil to paper time. So pause and get it done. Good. Okay, so some of you were like, Ms. Johnson, why did you give us so much time? That's good. I like it. So here, I'm just going to rewrite them. So x minus 5 parentheses x. I could write -0, but I'm not going to. And then I'm going to write x plus 2. So if you got that, awesome work. Then it says verify the factored form is equivalent to the standard form. How would you verify this is equivalent to this? What would you use? What would you use to verify that these are the same? What would you do? Yeah, I'd use Desmos too. Woo, woo. Okay, so I'm going to plug in, let me see. Let's just copy that one more time and then I'll put x's. X, oops, I need more space. X and x. And then you guys said it was parentheses x minus 5 close times x and then x plus 2. Was it x plus 2 someone? Yes, I think so. I hope so. Yeah, I think it was. Yay. Okay. So though that matches that and look at what happened. Look at it. Look at it. I'm very excited because this just shows me that I'm right. So I'm not kidding when I say that math is my favorite subject because I know that I'm right because I can check my answers. Are the results you found in problem 7 consistent with your fundamental theorem of algebra? Reminding you that the fundamental theorem of algebra says if I have a polynomial of nth degree, in this case, it's 3, that's my highest degree, I should have 3 roots. Boom, boom, boom. Yes, that's correct. It's true whether those roots are real or if they're imaginary. Okay. Okay, done with that. Here's another example. Use the graph to find the cubic. So this is something that I want you to try on your own. And then it says write it in factored form. Now you know how to do that. So I want you to try 10, 11, 12 on your own, but we're going to move on really quick. So it says we've seen the most basic cubic polynomial. This is what it looks like. This is what we call the parent function, x cubed. Explain how it's consistent with the fundamental theorem of algebra. So again, the fundamental theorem of algebra says, hey, Ms. Johnson, that's a cube. Why does it only have 1 0 at 0? Well, technically it has a 0 at 0, but that 0 happens 3 times. So I could write x is equal to 0, x is equal to 0, x is equal to 0, kind of like this, right? So do you agree with me that x cubed equals to x times x times x, right? And if I set it equal to 0, you told me earlier that I could just set each piece equal to 0. Do you see how I get 3 zeros? So x is equal to 0, x is equal to 0, and x is equal to 0. So, but Ms. Johnson, those are the same thing. Yeah, but I got it 3 times. So the fundamental theorem of algebra works. It's just telling you that's how many you should be looking for, especially in that case. Remember when you take the square root, right? When you take the square root. Okay, so here's another cubic polynomial for your consideration. Notice that it's given to you in factored form. Use the equation and the graph to find their roots. Now, if you notice, if you multiply x times x squared, you get x cubed. You should be looking for how many roots? How many roots should you be looking for? Very good. Someone says 3, Miss Johnson. Very good. So Miss Johnson, I only see 1. Why do I only see 1? Tell me, you guys tell me, where are the other 2? Where are my other 2? Yes, the other 2 are imaginary. So again, I want you to try this. Now here, I would definitely use SADMEP. And if you like think about the next step, you'd be like, oh, I get why it's imaginary, Miss Johnson. Okay. And then so that's pretty much it for this lesson. Okay, so I want to make sure that you guys are all comfortable. The biggest thing that you were supposed to get today is these are my roots. Oh, this is how you get to factored form. Got it. And this is my factored form. This is how I can get to my roots. So if that relationship in your head is super clear, you did today's work. Very, very strong work. Thanks for listening.